It's a great pleasure to introduce Frédéric Campana, who will speak on nilpotent quotients of quasi-K groups. Thank you.
Okay. So thank you very much for the invitation. I'm sorry not to be able to be there. So maybe we can start. So Rodolfo, are you scrolling there?
Yeah.
I don't think I can do that.
So we are talking about this project in common with Frédéric that it's called on nilpotent quotient of quasi-K groups. So let me make the setup. So we are going to consider a connected quasi-K manifold. And for this, I'm going to take a compactification and some divisor that is simple normal crossing. So in all this, we are going to assume that the quasi-Albanese map is proper, as in the work of Griffin, Green, and Katsarkov. That was the starting point of our investigation. So now we consider the Stein factorization of this map, and I'm going to suppose that Y is normal, and one has connected fibers, and the other Y are finite. So S has connected fiber, and B has finite fibers. So now we can also consider a smooth model of this variety, and so we can suppose that we can even factor this map, this Albanese map, through this smooth model. So we are going to divide the talk into two steps. One step is when the image is smooth, the image of this Albanese map is smooth, and the other one when it's normal. And so we are going to try to push the idea of the smooth to the normal case, and we will see what we get. So now we will have two surjective maps. So one is going to the smooth model, and the other one is going to the normal model. And now we have two theorems that says the following. That's the first one is supposed to be easier, is elementary, the proof. So the torsion-free nilpotent quotients of P1 of X and those of the smooth model of the Albanese image are the same. So this is known for X compact from the work of Frédéric. And now in theorem 2, we have the same conclusion, but we go until the normal the normal model of the image of the Albanese. Okay, so now we have this remark that says that theorem 2 says that the singularities of Y do not contribute to this nilpotent completion of this P1 of Z. Although in general, they do. Okay. So now let me recall some notation. So we are going to denote the lower central series GK, defined in this way. So the first one is G, and then we define in an inductive way. But we are actually interested in the torsion-free lower central series. So we are basically killing the torsion of these groups, and then we denote by GK prime the kernel of this map. And then we write G-nilp, this quotient, the group, by the intersection of all these lower central series torsion-free. And this is moreover going to be functorial. So when we have a complex space, we can associate to it an nilpotent Galois cover, Galois, and the deck transformation group is going to be this nilpotent completion. This is also to be functorial. And now we have a reformulation of theorem 1 and theorem 2. So the induced map in the nilpotent completion that we have first in the smooth case.
Your opponent Galois cover. What's his precise definition?
Sorry. So yeah, when you have a quotient of your fundamental group, you will have a Galois cover associated to it, right?
Okay, so you mean the group corresponding to the Nilpotent quotient?
Yeah.
Oh, okay,
Yeah.
okay.
And so the theorem 1 can be restated as this. When you have the smooth model of the image of the quasi-Albanese, so this is an isomorphism. And moreover, the theorem 2 can be stated as follows. So when you have the map with the normal image of the quasi-Albanese map, is also an isomorphism. So this holds if X is smooth and quasi-projective. So the X is always smooth. And now as a corollary of this, we get that the nilpotent cover of X is the fiber product with this nilpotent cover of this normal subvariety. So we have the theorem that was proven by Katsarkov when X is projective, and by Green, Griffiths, and Katsarkov in the quasi-projective case, that the fibers of this map have connected components, and that the X nil is holomorphically convex with this Remer reduction if X is quasi-projective. So we obtain a new proof of the result of Katsarkov. And Mark Green spoke of this on Monday, but we are also talking in the quasi-projective case. So now we have some applications of this first theorem of the easy one in the sense of special manifold of Frédéric. So the definition that we are going to give here is a short one, even if we don't give much more details. Ja has given some notions yesterday. So if we have a quasi-Kähler manifold, we said that it is special if the Kodaira dimension of a completion with L is strictly smaller than P for each rank 1 coherence subsheaf of the logarithmic P forms on X for any P. So the intuition is that it doesn't admit a fibration onto something of general type, but this is really rough. And now, if we consider this line bundle, the determinant plus the divisor at infinity, and we define the logarithmic Kodaira dimension in this way, we have the following theorem. So if the logarithmic Kodaira dimension of X is 0, then we have that X is special. And Frédéric has also some generalization of this that is called W slope rationally connected. So the definition of this is here. I'm not going to read it, just to go over. And then we have the following proposition that it's due mainly to Kawamata in 83. So we have that if X is special and quasi-projective, and we are also assuming this main assumption that we had before, that the quasi-Albanese is proper, then we have that it's going to be surjective and with connected fibers. And thus we have proved that using theorem 1, that this has the same, that the smooth image has the same nilpotent quotients as the original variety. And therefore we have that Z equal to Y equal to Albanese. And now in this case, the quotients of a special variety are always abelian. So Ja has spoken yesterday of a case where this fails, but in this case we are assuming to be proper the quasi-Albanese. Now this is what I was saying. So if you have this is the corollary of theorem 1 with this proposition that the P1 nil in this case is It's just H1 modulo torsion. Now, Frédéric has a conjecture in that if X is compact Kähler and special, then pi1 of X is virtually abelian. And this is known for linear quotients. But this can fail if X is non-compact and the quasi-Albanese is non-proper. So in the work of Cadorel, Deng, and Yamanoy, they show that this can be nilpotent. We have also some simple examples of this. But the abelianity conjecture then can be restated as the nilpotency conjecture as follows. So if X is quasi-Kähler special, then pi1 of X is expected to be virtually nilpotent. So Jan has spoken yesterday of some proof of this when this admits a linear representation. So now let me just comment that if you ask more, if you have W slope rationally connected, then you can expect the abelianity conjecture, but let me not be precise on this. Now, we want to give some examples with non-proper quasi-Albanese maps and make some remarks on this abelianity conjecture. So let me give the examples as follows. We consider a line bundle L. So if we have a line bundle L on a quasi-projective manifold B, and we consider B prime to be the zero section of this line bundle, we denote by X the projection of this bundle, but with the zero section removed. So we have a C star bundle, and this is going to give our example that we are searching. So now we can use the Gießen exact sequence, and it's going to read as follows. And the last map is going to be multiplication by the first Chern class. So if this Chern class is non-zero, we have that the Betti number is actually the same as the one in the base. So we are having a central extension, and this is going to be torsion-free nilpotent. So it's this pi1 of B. So if we choose this pi1 of V to be torsion-free abelian, the nilpotency class of pi1 of X is going to be 2, and pi1 of X is not going to be virtually abelian. So the simplest case, we can take B equals C star times C star, or an elliptic curve with this. And moreover, we have that if the log canonical bundle of B is trivial, then we are going to have the same for X. And well, this contrasts the difference between compact Kähler and the open quasi-Kähler cases. So if we consider the Albanese map of this variety is going to be basically this B. And we are going to have non-compact fibers. So this is also contrast with the corollary that we had before in the special case. So now, as I was saying before, in the Kähler case, we have the abelianity conjecture, and if we have first Chern class equals 0, we have virtually abelian fundamental groups. And now in the open case, we see that they can see torsion-free nilpotent, but not virtually abelian. So it's something different in the open case. So now there is also some notation that I will revisit here. So we will denote by a nu G the nilpotency class of G. And now we have the nilpotency class of the fundamental group. And if we have a subvariety of X, we will write by pi1 of F lower X the image of this subvariety into the fundamental group. And now we can write the nilpotency class of this F as defined by the nilpotency class of this image. Now we have the following theorem. If we have a fiber space X to Y, and we have X to Y projective manifolds, then F, and if F is any smooth fiber of F, then we have that the nilpotency class is the maximum of these two nilpotency class of the fiber and of the orbifold base. So this is very special for projective manifolds. So it's not true in the compact non-Kähler case, where the maximum becomes the addition. So in particular, if we have that the fiber and the base are virtually abelian, so we have the same result for the pi1 of x. And so this no longer holds on the open case. And we have also this remark here that we have only two-step torsion-free nilpotent quasi-Kähler groups are known. So we wonder if there are higher step nilpotent. So this is we leave as an open questions. And we have more remarks on this compact versus open. So we have that solvable Kähler groups are virtually abelian by a result of Del Sand. And we have the question that if this remains true for the quasi-Kähler groups. So this is true for polycyclic by Arapura and Nori in 99. So let me, okay, do you have questions, remarks, Frédéric, something that you want to say?
No, that's okay, that's okay.
Okay, so now let me go into the proof of the first theorem. So remember that the first theorem was when the image is supposed to be smooth, or we take a smooth model of the image. So now we wanted to use the same strategy as in the compact case. In the compact case, Frédéric used this proposition of Stalin that says the following: if you have f from x to y, a continuous map between CW complexes, and we assume that the induced map in homology is isomorphic for I equal 1 and surjective for I equal 2, and that this homomorphism in fundamental group is surjective, then the nilpotent completions are isomorphic. And so basically it's a game into H1 or H2. And Stalin, in order to prove this, he considered the homology exact sequence for a quotient of a group like that. And then he considered the induced maps, and then he can conclude by using this hypothesis in an inductive way. He goes by proving the n by n step in the nil quotient, in the nilpotent quotients, and then he considers at the infinity. Okay. So now when we have a quasi-Kähler manifolds, and we have a proper surjective holomorphic map between them, we have the following result. So the map induced in cohomology is injective for any K. So this is classical when the results are, when the manifolds are compact, and we extended this in some, let's say, almost easy way. For the quasi-Kähler, it still holds. So, however, this lemma fails when Z is normal. So our strategy for proving this, the theorem 1, was to use this Stalin's lemma. And then we have the property of the Albanese that the image has the same H1, but now we want to use H2. Okay, so for H2, we can use this lemma. In the compact case, as I was saying, it was known, and then we prove this, and we have the proof for the theorem 1. But if we want to extend to normal case, this can fail. So if we take Hilbert surface, then you have some points that are going to, well, you will have some in H2 some weight 1 coming from the resolution of singularities of some points there. So you can, all the weights that are below Q are going to die in the pullback because you have a smooth X. So this was pointed to us by Robert Latterbeer. And so we cannot use this Stalin's lemma. We need to use something different. And this is what we are going to do in theorem 2. So in theorem 2, we are going to use the same idea, but different tools. So now, to get this, we're going to use the mixed hot structure on the Malchev-Lie algebra of algebraic varieties constructed by Hein and by Morgan. So the starting point was a paper of Arapura, Dimka, and Hein from 2016 that says the following. So their idea is that when you have a normal quasi-projective variety, their fundamental group or their topology is in some sense close to the smooth case. So we are taking this theorem that says the following: the Malchev-Lie algebra of P1 of Y for Y and normal algebraic variety takes the following form. So you have that there is a quotient from the H1 of Y by some image, some delta image of the weights of the graded parts in H2. So you have this image in the free Lie algebra generated by this H1, and then if you quotient by this image, you get the Malchev-Lie algebra. So this is a morphism of graded vector space, and then it's functorial. So we are going to use this. And this was stated in Hein in 96 for Y smooth, and then he remarked that it can be extended to the normal case. So it's in some case due because when you have a normal variety, H1 of Y will have only weights as if it were quasi-projective. So H1 cannot see the singularity, something like that. And so if we consider a resolution of singularities in this Y, and we have the morphism in pi1 is surjective. And so we also have a surjective morphism on H1. And as I was saying, this will only have weights as if it were a quasi-projective. So this is interesting. So now the main upshot of this is that if we have the quality of these kernels, we have two maps. One going from Y to the Albanese, and one going from Z to the Albanese as well. But if we have that the kernel of these are the same, then we can conclude using this theorem that the nilpotent completions are the same. So in the projective case, this is pretty easy once that we know that this is true by a result of the linear. So we have a result of the linear that is 8.2.7 that says exactly this, and that if you have three maps such that this one is projective, this one is smooth, and this one is also smooth, then we have exactly this equality of kernel. So this gives another proof of the result of Ludmil in the projective case, and we want to extend this to the quasi-projective setting. Now, let me go. So the theorem of the proof of the theorem 2, we are going to search for this equality, and this is going to be divided in two parts. So the first part is going to be for the weights 3 and 4, and yeah, so we have to check it for 2, 3, and 4. We are going to check first for 3 and 4, and then at the end we are going to check for the weight 2. Now, we can take the graded parts in this map, in the induced map, and we can see that this is going to be injective. And the proof is as follows. So we go by induction. So if this has a dimension 0 or 1, this is going to be easy. And then we can use two things. So we can use the linear 3, or we can use the book on Hodge theory of Steinbricks. And we have a Mayer-Vittori sequence. So we need to take a discriminant square. We need to take a resolution of singularities, and then the discriminant, and then the exceptional divisor. And this is going to give us a Mayer-Vittori sequence in the following way, like this, with the following notation. So we have a proper modification with discriminant D, and this is going to be the exceptional divisor. And now we apply the graded parts, and if we apply it to this sequence, we know that H1 has only weights, can only have weights 0, 1, or 2. So if we are above this, then this term is 0, and this is going to be injective. So if we have that this part is also injective, then we have the injectivity of this resolution of singularities. And then we prove also this injectivity via by induction. And then we use also the smooth case. And now in something like that, we prove the weights 3 and 4, and what is left is the weight 2 case. So now, until here, we have only used the normality of Y. So we have not really used the properness that we have really assumed, and this is going to play a role in the last step. So we are going to consider a suitable compactification of all the main characters playing a role here. So we have a small model of the image, the normal model of the image of the Albanese and the Albanese. And we can take compactification of these varieties, and then we consider a diagram like this, induced by the trivial morphism between them. So we are going to have here some way to maps, and these are going to be surjective by the linear 2. So as A and Z are smooth, we have that the weight 2 part of this open variety A and Z, they come from the compactification. So we have that these two maps are surjective. And now, what I wanted to show in the proposition that I left some page behind, we wanted to show that two kernels were the same.
No.
So, yeah, sorry.
Yes, this is known. What we want is the next one.
Okay, sorry, yeah. So this come from the linear 3. Okay, yeah, sorry. So this A prime and A prime D prime, this is the same result that we used before, that says that when you have some compactification and some singular variety inside a smooth one, then the kernel is the same. Sorry, yeah. So this is from the linear tree. And what we want was really some equality of some kernels. And what we see from here is that the quality of some kernel in this left side, they are going to be actually equivalent to the kernel on the right side. But on the right side, we can use some diagram chase, and here we have some projective varieties. So we can use the hypothesis that the quasi-Albanese map is proper, and now we have some information about this. So this is what I'm going to explain in the next slide. And so this is the following. When you have a smooth quasi-projective, you have that, if you denote by this L here, this is the kernel of this map, and remember that this is smooth. So you have some Gaussian map, and this L is the space of H2A bar generated by the Chern classes of the irreducible components. So this is known, and the same for K, because K here is also the kernel of a smooth variety. So now, as you have the Albanese map that is proper, then you have that the divisor at infinity is going to be the pullback of this composition of the divisor at infinity of the Albanese variety, of a compactification of the Albanese variety. And then you have also the same statement for the for only the normal variety. So we are using here essentially the property that this morphism is proper. This does not hold if the quasi-Albanese map is not proper. And then using this, we can show that if you pull back this K, then you will have that it will contain K prime. So the K prime was the one in the middle, and we were searching to have some equality between the kernels. So now that you have some contention, you will have that the vector subspace of H2 bar is generated by these C1s of the components in this divisor at infinity and Y. So in this form, we can conclude using some contentions that actually what we have, the kernel is essentially the same. And so when they are the same, we can use this proposition of Hein now, and then we can conclude that the nilpotent completions are the same, even in this normal case. So just let me recall once more what we did here. So we were interested in the weight 2 part, and the weight 2 of H2. So we had some compactifications of everyone, and then we can use that this part comes from the compactification. And now we know that in the compactification case, the kernel of this is also the kernel of this composition. This is essentially due to the linear, and then applying the whole of this, we can show that the kernel of this is actually the kernel of this composition. And so we conclude by using this result. And I think that's the talk. I went way too fast, so I'm sorry for this.
Okay. If there's no further comments, so thank you very much for the double talk by Frédéric and Rodolfo. It was nice. Thank you.
Bye.